This lesson will be looking at the law of multiple proportions. The law of multiple proportions states that if two elements, A and B, combine to form more than one chemical compound, then the various masses of one element A, which combine separately with the fixed mass of the other element B, are in simple multiple ratio. What is the law saying? Sometimes you may have elements A and B combining to form a compound C. Some other time, the same element A and B they combine instead of forming compound C, they form a different compound entirely compound D. So the law is saying that if that happens, then the various masses of one element A, which combine separately with the fixed mass of the other element B, are in simple multiple ratio. Good examples of elements that combine to form more than one compound. We have some example here. Copper and oxygen can combine sometimes to give copper 2 oxide or copper 1 oxide. These are two elements, copper and oxygen. Depending on the condition of reaction, the reaction may lead to the formation of copper 2 oxide or copper 1 oxide. Also, iron and oxygen can combine to form either iron 3 oxide or black iron 2 oxide. You look at the same element. In one condition, they combine to form a brown iron 3 oxide. In the other condition, they combine to form a black iron 2 oxide. Also, iron and chlorine can behave like that. Sometimes iron and chlorine will combine to give us a brown, yellowish iron 3 chloride or a green iron 2 chloride. And then lastly, lead and sulfur can behave in the same manner. Sometimes lead and sulfur combine to give us a black lead 2 sulfide. Some other time they give us lead 4 sulfide. And so the law of multiple proportion is saying that the various masses of the first element, which combine separately with the other one, are usually in a simple multiple ratio. And to verify this law, we are going to find the percentage by mass, the mass of copper in two samples of copper oxide. One of the oxide is copper 1 oxide, the other one is copper 2 oxide. So we are going to reduce both oxide to obtain the mass of copper in copper 1 oxide and copper 2 oxide. When we were doing experiment for verification of law of definite proportion, we make use of copper also. Yes, we reduce copper to copper residue, copper oxide rather, we reduce it to copper residue. So we are going to use the same setup to verify this law. By reducing copper 1 oxide to copper residue, we also reduce copper 2 oxide to copper residue, and then calculate the amount of copper that is found in both oxide, that is copper 1 and copper 2 oxide, respectively, to see that if they are actually a simple multiple ratio according to this law. Now, when we say simple multiple ratio, what does it mean? For example, if you have 1 gram of copper in one of the oxide, then the other one should be 2 grams. If you have 2 in one, the other one should be 4. If you have 3 in one, the other one should be 6. That is what they mean by simple multiple ratio. So we have two oxide for the amount of copper present in both. So I have a simulation here on that. So this is my weighing balance. Just to give you an idea of what's happening in the lab. I'm going to weigh two empty container. Okay, the weight of this container is 6 grams. Then that is my copper 2 oxide placed on it. So the total mass here is 7.9, but the mass of this empty bowl before copper 2 oxide was placed in it, the mass was 6 grams. So if the reading right now is 7.9, therefore the mass of copper 2 oxide is 7.9 minus 6, which is 1.9. Then this is copper 1 oxide. The copper 1 oxide, the reading right now is showing us 8.9, and the mass of this empty bowl is 6. So 8.9 minus 6, which is 2.9, give us the mass of copper 1 oxide. Now we're going to reduce these two samples of copper now. This black one is copper 2 oxide, and this brown, yellowish kind of is copper 1 oxide. So This is a glass tube. We are going to heat this glass tube with the sample inside. And now, as we heat it, we direct a stream of hydrogen through the tube to reduce the copper 2 oxide and copper 1 oxide to copper. We want to get only copper there. So we are carrying out a reduction reaction. And this hydrogen gas is coming from this conical flask here on the left hand side. The conical flask is a mixture of hydrochloric acid and zinc. We know that when hydrochloric acid reacts with zinc, hydrogen gas is given up, which is a method of preparing hydrogen gas in the lab. So we have a mixture of dilute hydrochloric acid and zinc in this conical flask. So the zinc metal will dissolve in the hydrochloric acid. As it dissolves, it releases hydrogen gas. Heat up the glass tube and see hydrogen gas is passing, which is represented by that arrow that is flying through the glass tube. So as we heat it up, passing a stream of hydrogen gas, this copper oxide will reduce to copper. Okay, we are done with the reduction reaction. So what we have left now in those glass bowl is, sorry, the labeling is still showing copper oxide. This is supposed to be copper residue now, not copper oxide. So, and even the write up here too, I made mistake there. It's copper residue now because we have carried out reduction reaction. There is no more oxygen there. What you have left is copper. So the mass of copper in copper, the mass of copper residue in copper 2 oxide is 7.4 minus 6. 7.4 minus 6 because what we have on the reading here is 7.4, but the mass of this empty bowl when nothing was inside is 6. So to get the mass of copper residue, we need to subtract the mass of the empty bowl from this 7.4 that we are reading right now, so that the mass of copper residue is 1.4 gram. Then this is the copper from the other sample, that's copper 1 oxide. So mass of copper residue from copper 1 oxide, the reading right here is 8.5, 8.5 minus the mass of this empty bowl, which is 2.5. Okay, so now that we have the values of copper in both oxide, we can now calculate to see whether the masses are actually a simple multiple ratio. So for the first sample, which is copper 2 oxide, the mass of copper oxide as we weighed then was 1.5 gram. That is before reaction. Before reduction, mass of copper oxide, that is copper 2 oxide, is 1.9 gram. Then after reduction, the mass of copper residue was found to be 1.4 gram. That means mass of oxygen will be 1.9 minus 1.4, because this 1.9 here is mass of copper oxide. Copper oxide is copper plus oxygen. So if copper oxide is 1.9, now we have reduced that copper oxide to have only copper residue. So to get the amount of oxygen, we need to subtract this 1.4, which is the mass of copper, from the mass of copper oxide. The 1.4 minus 1.9 minus 1.4 rather is 0.5, meaning this 0.5 gram of oxygen copper to give us oxide. So if that is the case, then what we 1 gram of oxygen combined with 1 gram, that's 1.0 gram of oxygen, we combine with x gram of copper. So that by simple proportion, x is equal to 1 times 1.4 divided by 0.5. Let's use a calculator there. So 1.4 divided by 0.5 is 2.8. 2.8 gram. That means 1 gram of oxygen we combine with 2.8 gram copper. And you can round this to the nearest whole number. That will be 3 gram in copper 2 oxide. Let's do the same thing for copper 1 oxide. Now when we measure the oxide before reduction, the mass was 2.9 as mass of copper 1 oxide. Then we carry out reduction to obtain copper residue, and the mass obtained was 2.5. So that mass of oxygen will be mass of copper oxide minus mass of copper residue, and that is 2.9 minus 2.5, which is 0.4. So this 0.4 is the amount of oxygen in copper 1 oxide. So if 0.4 gram of oxygen combined with 2.5 gram of copper to give us 2.9 gram of copper oxide, copper 1 oxide, then what will 1 gram of oxygen combined with, let it be X. So by simple proportion, get the value of X by cross multiplication. So that X equal to 1 times 2.5 divided by 0.4, which is 2.5 divided by 0.4 is 6.25. 1 gram of oxygen will combine with 6.25 gram of copper. Rounding this to the nearest whole number, that is 6 gram. So you can see now, for copper 2 oxide, the mass is 3. That is copper is 3. Then copper 1 oxide, the mass is 6. Of course, what is the difference between 3 and 6? That is a multiple. 6 is a multiple of, that is what the law of multiple proportions is. That, where is the law? If two elements A and B combine to form more than one chemical compound, then the various masses of one element A, which combine separately with a fixed mass of the other element B, are in simple multiple ratio. So in this case, what is fixed here? Oxygen is fixed because we are using 1 gram as a standard in both oxide. As after our analysis, we have 0.5 gram of oxygen in copper 2 oxide and 0.4 gram of oxygen in copper 1 oxide. Now we are taking a standard of 1 gram, so that if 0.5 gram combined with 1.4 gram of copper, then what would 1 gram of oxygen combine with? By our calculation, it is 3 gram. Then we do the same thing for copper 1 oxide. Our analysis shows that 0.4 gram of oxygen combined with 2.5 gram of copper. Then while with this 1 gram of oxygen combined with, by calculation, it is 6 grams. Of course, that means the ratio of copper in copper 2 oxide and copper 1 oxide is 3 to 6, which is 1 to 2. And then the law of multiple proportion is verified. Since the mass of copper, which combines separately with a fixed mass of oxygen in copper 2 oxide and copper 1 oxide, are a simple multiple ratio of 1 to 2, then the law of multiple proportion is verified.